Hi everyone. So, this is lecture number 13. In the last couple of lectures, we introduced the idea of negative numbers. And based on that, we expand our number systems from natural numbers to integers. This is actually a big deal, because along the process, we were able to kind of just complete the definition of subtraction. Before we introduced the negative integers, we had difficulty to properly define certain type of subtraction over natural numbers. In particular, we had the issue if we have a larger number being subtracted from a smaller number, which would result something that we could not even understand what it is if we merely had natural numbers only. So it was quite natural to have the concept of negative integers in order to answer that question. So along the way, we were able to complete the definition of subtraction. But it's very important to understand we kind of carefully introduce those concepts one by one through rigorous definitions. So nothing should be taken for granted. When we study arithmetics in earlier grades, you took all those things as given. Your teachers taught you how to do certain things. But unfortunately, it would be too difficult to explain why those things work. So in this class, in Free Asian Math grade 5, in this year, we took the advantage of certain quite advanced mathematical concepts. We took some pages from college level math materials and carefully select certain things to just make them understandable to even elementary school students. So in particular, we first introduced the concept where the natural numbers came from. That was from counting. And based on that, we developed addition, which is again based on counting. Then we developed subtraction, which is the inverse of addition, but we had some difficulty like we just discussed. In order to overcome this difficulty, when you cannot subtract a large number from a smaller number, we expand our natural numbers into integers. That way allow us to completely define what subtraction should be. So given any two integers, you are able to perform subtractions. Doesn't matter what those integers are. There's no restriction. Both non-integers can be negative, or one of them is negative. So before we start today's lecture, let's have a recap of what we have in the last couple of lectures. It's very important to understand nothing should be taken for granted. Okay, so we introduced some operators. Basically, we borrow our ideas that were used in the natural numbers and accounting, use the increment and decrement operations with little cases. Then we expand those operators for natural numbers. Those two capitalized operators are exactly the same. In other words, when we increment or decrement natural numbers, except decrement 0, it doesn't matter whether you have a little case increment or uppercase increment or decrement. They're all the same. However, once we want to do decrement at 0 or cross 0, we have to carefully define what that means. So capital decrement 0 give us a -1. And then we will continue to do that to get all the negative integers. That's where the negative integers came from, or how we define them. Based on that, the increment, capital I increment, is just the inverse of decrement. So now with those two capitalized operators, we are able to increment, decrement for any integers. It doesn't matter. Across all the whole number line, we are able to do increment or decrement for any integers, whether positive or negative. Now we introduce all the important concept of negation. Because we have already properly defined what the negative integers are, which is essentially based on the decrement operation starting at 0, right? So this is a little bit. So, oops, this is 200 and you get 100. Okay, so let's not do this, it's too big. Okay, so on the number line, we start at 0, we do decrement, decrement, remember now it's capital decrement. That way give us all the negative integers and so on. So on the right hand side, we got 1, 2, 3, 4. And it's very easy to see that, say, what do we mean by -2? -2 is decrement twice from 0 to the left hand side. And what is 2? 2 is increment twice from 0. Therefore, we can easily see that -2 and 2, or for any numbers, if we replace 2 with, say, another natural number m, -m or m, they are equal distance from 0. Meaning that the distance from the -1 should be the same as distance between 0 and the positive version. So therefore, we were able to introduce this important negation operator. It's very important to understand that this sign, this symbol in math has been overused or abused. So it actually means two different things. One is a subtraction operator, meaning that you need two operands, two numbers to perform subtraction. Subtraction always needs two numbers. And another meaning of this symbol is the single operand operator, which is the negation operator. So, in summary, we have certain properly understood properties. So why is that decrement and increment, they are pairs? So if you have a number integer m, you do add another number n, but decrement on that n, it's the same thing as you first add n, then do the decrement. Or if you want to subtracting the decrement of n, you can do subtraction first, but do increment after the subtraction. So where here n is a positive integer. Okay, so that was the kind of lemmas, we call them series, we should call them lemmas. That's how we're used. And then we came with this negation operator. Because of this symmetry we saw, we were able to properly define what is the negation operator. So if we have a positive integer m, the negation of this positive integer would be -m. So that is that if we have 2, negation of 2 is just, this is negation of 2. is just -2. Okay? That's why we can write -2 without these parentheses. Essentially, -2 is the same thing as negation 2. Okay, because of that, we can further negate a negative integer. So, what is the negation of -2? Well, it just flip it. Then it becomes 2. Why this is 2? This is very important to understand. This is just the definition. Because negation is just an operator, and we need to properly define how this operation works. When the number being operated on can be both negative or positive. When we define this, we only define this operation for what's inside this parenthesis to be positive integer. But we can further define when this number inside the parenthesis, what happened if it's negative. We define when this integer is negative, then we perform negation, it becomes positive. That's actually how we define this. And this definition makes a lot of sense. So it's always important to understand this is just a definition, nothing else. Okay? In other words, this negation operator is just like a reflector. Whenever you have an integer on the number line, whether it's on the right-hand side or left-hand side of 0, whether it's positive or negative, the negation is always an integer on the other side, which is equal distance from 0 as the current integer. Okay? It's just a mirror image. So, in other words, this negation operator is just like a mirroring operator or reflecting operator. Okay? So that's just the definition of this. And based on this, we were able to define, based on those concepts, we were able to define addition and subtraction of any given two integers. Remember, we achieved this through two steps. First, we consider what happened if the number being added or subtracted is a negative, a natural number. So we first, without consider the second number being negative, we first only consider the second number is a positive or 0, a natural number. But we do relax on the first number. We allow the first number to be any integer. That's how we started with this definition and this definition. Definition 1.11.1 and 1.11.3. So in those two definitions, we allow the first number to be any integer, but the second number is still a natural number. And their definition, this subtraction or addition, almost exactly the same as our natural addition or subtraction, natural number addition or subtraction definition. The only difference is that now we don't really care whether the first number is a positive or negative. It doesn't matter because definition is still through increment and decrement. But now the increment, decrement are capital cases. Okay? So for example, when we do definition for subtraction, we start with m and we perform n times of a decrement. Because the decrement now is capital decrement, we can easily go across 0 and go into the negative half on the number line. And for addition, it's just the business as usual. We do counting forward or counting toward the right n times. Okay, so this is the first step. Now the second step is that we now consider, we further relax on the second number. Now we allow the second number to be a negative integer. So what happened when we allowed the second number to be negative integer? Well, now the definition, it just got a little bit twist. Still based on fundamentally based on our idea of counting forward or counting backward. Okay, so if m is any integer, but now you add a negative integer, negation of n is a positive integer. Negating n, after negation, is a negative integer. So m plus negative n is nothing but we treat it as m subtracting a positive integer, right? So you can see that the two definitions are essentially the same. Okay, this is very important just for the next topic and the next theorem that we will prove after this review. So when we do m plus a negative integer, it's essentially the same as we subtracting a positive integer in the first place. You can see that because the definitions are all the same. So we perform m subtracting 1, subtracting 1, subtracting 1, perform this n times. And for as to the final definition, this is a little bit tricky because now we want to subtract a negative integer. And the definition is the same as if we want to add a positive integer. So m subtracting the negation of n is defined to be the same as m plus n. So m plus 1 plus 1 performed it n times. Okay, this is very significant because we will see how this will help us to prove the next theorem that we will see. But for now, you should understand all those are definitions. And we gave a detailed explanation for the motivation of the last two definitions. You need to carefully review our last lecture to understand why we could and we want to define those two in that way. Essentially, it's just counting. Fundamentally, it's just counting. Okay? Based on the fact that what happened when our definition extended, say, m minus m, if n is a positive integer, and we gradually reduce this m minus 5, m minus 4, m minus 3, m minus 1, and finally nothing, or m minus 0. But if we keep reducing this number, what is m minus negative 1? And what is m minus negative 2? Because we see that each time when we reduce the number being subtracted, the result actually goes up. So we expect this to continuously go up if we reduce 0 to negative 1. And that gave us the motivation for such a definition. Okay? So once we have those definitions, look at what we have. We have 4 separate definitions. Together, they cover all the cases for addition and subtraction, and of only just any integers. It doesn't matter the number or second number, whether they're negative or not. We don't really care. We covered everything with those definitions. So it's really significant to understand why we took such a pain to define something that you might have learned how they work. But this is get to the bottom of the thing. We define those operations to be this way. Okay, now with that, we are able to prove easily a theorem. Okay, so we mentioned this at the very end of the last lecture. So theorems for adding and subtracting negative integers. So here on top is the number line. And now we want to prove this theorem. It has two subparts. So essentially looks very simple. M plus negation or negative m equals to m minus n. What is the difference between this and our definition earlier? We want this theorem to be as inclusive and general as possible. So we don't know the sign of neither m or n. So you cannot just say, because it's written this way, you assume n is positive. So n could be negative. That's why we say for any integers m and n could be positive or negative. That's just add a little bit thing for us to prove for this theorem. Otherwise, it's nothing because it's right in the definition. So the next subpart is if you subtracting the negation of an integer, m subtracting here negative n, well, we should say negation of n because we don't know whether n is positive or negative. So when we say negative n, we are really saying negation of n, okay? Because remember, this negative sign is actually, we had already expanded into an operator. It's the negation operator. So this theorem says that when you subtracting the negation of integer n, the result is m plus n. So this is not axiom, this is a theorem. What does that mean? Well, it means that we need to prove it. We cannot just claim this makes sense, and I have done quite some, positive, negative addition or even subtraction. I know how this works. I think this is right. No, you cannot do that. If you have something that is not an axiom, you have to prove it. And the proof will be based on either some definition or some axiom or some already proven theorem. So let's prove those two results. Okay? So the first result is m plus the negation of n equals to m minus n. Proof. How do we prove this? And what is a proof? Well, at this time, for this year, you don't need anything you have nothing to prove. All you want to do is to read some proof. So next year when you are in grade 6, you will be in the position to write some simple proof for some problem all by yourself. It's very important to develop this kind of mathematical capability. Math at the end, if you go to college, go to graduate school, you will just need to, most of the time, you just need to prove problems. Also, you will run some special just math branch like numerical analysis. You may need to find some just using computer to perform some very difficult calculations, but basically for higher math you will be doing proof-based problems. Okay, so how do we prove this? What do we mean by proof? We just need to prove whatever we mean on the left-hand side of this equation is indeed equal to whatever we mean by the right-hand side. Okay, we just need to prove this is actually true. So before we write proof, we need to put a question mark on this equality sign. Is this indeed true? Okay, let's do the proof. So we will have to do this combined with our second one. Put all together. What is second one? If you subtracting a negation n would be n plus n. Because the two are so closely coupled, our proof actually will be easier if we do 1/2 of both first, then do the second half. And what is that 1/2? Okay, so this is the two statement that we want to show. We want to prove the two all at once. So first step, assume n is positive. Okay, now we classify based on the value of n. We assume n is positive. Okay? So in that case, what is n plus minus n? Well, we have to go back to our definition of n plus negation of n, where n is a positive integer, right? Otherwise, we don't even know what it is. What is this? N plus negation of n. We go back to our definition. It's right here. It's definition 1.12.1. Okay? So, n is an integer, any integer, but n is positive. And we define n plus negation of n as m. This equals to n minus 1, minus 1, minus 1. And we do it n times. This is by definition, right? By definition. But look, this definition is essentially the same as definition 1.11.1. And what is that? This is exactly the same as what we had in this definition equation 1.16, right? So this is just by definition just n minus n, where n is a positive integer. Now you see why we need to take two steps to define even addition for integers, because it doesn't matter whether the number being added is positive or negative. With positive, we were able to just go back to a definition where it's just natural, like subtracting a natural number. So this is n minus n. So we are actually done for this part. How easy is that? Whether this is true, it is true if n is positive. Okay? But at this time, we still have a second part that we have not proven. Okay, so we are done for the first one when n is positive. Now for the second one, we're subtracting a negation of n where n is positive. What does this mean? Well, again, we have to go back to our definition. It's right here, 1.12.2. This definition tells us that this equals to m plus 1 plus 1 plus 1. How many times? We do it n times. This is again by definition. But now you recall, what is this? This looks so familiar. This is even just like the natural numbers, right? M plus 1 plus 1. This is once again, by another definition, this is exactly the same as m plus n, where right here, 1.11.3, oh, this is the definition when we add a natural number to an integer. We don't know whether m is negative or positive, we don't care. But we do know when you have integer m, you plus 1, do it n times, because n is positive or natural number, we can say you can do it n times. But this is our very definition of how to add a natural number to an integer. So once again, we are done. We say this is also true, just like we did in the other case. So where n is positive, the two subparts are true. And in both cases, that's because we already define them to be true. Okay? So nothing to actually prove, because those are just definitions. But this is only for the case when n is positive. Now, what else could n be? Well, our second case will has to be when assume n equals to what? 0. Remember, when you discuss an integer, you always have to consider 3 cases: positive, 0, negative. 0 is special, but special case usually is very easy. So if n is 0, then m plus negation of 0. What is negation of 0? Negation of 0 is just 0, and m plus 0 is just m, but this is also the case as m minus 0, right? So once again, so this is the same as m minus n, if n is 0. Similarly, m subtracting the negation of 0, that's once again just m minus 0, so it's m and equals to m plus 0 and equals to m plus n, because n is 0. So just a lot of just arithmetic, but nothing at all, because we are just dealing with 0. You're subtracting or just adding a 0, negation of 0 is 0. So nothing happens actually. So once again, if n is 0, both statements are true. M plus negative n equals to m minus n. M minus negative n equals to m plus n. So we are done with this second case. Now third, this is a little bit more interesting. Third, assume n is a negative integer. After this, we have covered all the cases for n, whether it's positive, negative, or 0. So what happens when n is negative integer? First of all, we consider what do we mean by that. So the first one is m plus negation of m, right? Well, the difficulty is now we know n is a negative integer, so we are adding negation of a negative integer. That makes the arithmetic a little bit difficult to understand. But we will do something very clever, but very, very basic in algebra. because n is a negative integer, what can we do? We write n as negative k, where k, well, I hesitate to write this, but for notation, we just write that k is greater than 0. We have not formally introduced what is this sign greater than, but just want you to know this is nothing but saying that k is a positive integer. Why we can do that? Because that's the definition of the negation operator, right? We know negation is just the negative sign when it applies to a positive integer. So because n is a negative integer, we can write n as negation of k. For example, if n equals to -5, we are simply saying that n equals to negation of 5. Put 5 into the parentheses. Does that make sense now? Okay, so n is negation of k, where k is actually the positive portion of this negative number, which we would call absolute value. But for now, don't worry. We just understand n is negation of k because n itself is negative. So k has to be a positive, right? Here, k is 5. Now with this, we call this kind of auxiliary thing. And this is very important in algebra, which helps us to manipulate things. Okay? So with that, what is m plus negative n or negation of n? This equals to m, because n is negative k or negation of k, we can write this. Right? We substitute n equals to negation of k into this n, into n. But look, what is this? We already say that negation of negation goes back to, it's just reflecting. It's just that mirror operator on the integer, on the number line, remember? It's just, you do it once, you flip to the other side of 0 on the number line. You do it twice, it goes back to yourself. And it doesn't matter where you start. You start with a positive or you start with negative, doesn't matter. You do 2 flipping about 0 on the number line, you go back to yourself. So magically, when we have this, we truly know this is just m plus k. Okay? So, but what is k? Remember, we are trying to do this. Okay? So, k is just the negation of n. So, on this number line, we will see that m plus k is really just m m plus k is just m plus 1 plus 1 plus 1 k times. But this is really already proven by our earlier result, where is this version when n is positive, right? This one, I'm sorry, this one. Remember this? If you have n is positive here, we already proved this one. In other words, now, the version we try to prove m plus a negative n is just really, this version is exactly the same as what we did just here. Remember, what is this? This is the second part of the theorem, but when n is a positive integer. And we know you're subtracting the negation of positive integer, that equals to m plus that positive integer. And that's exactly what we are trying to see here, right? So, in other words, when n is a negative integer, m plus this is exactly m subtracting n, where n is negative k. Because of this, this is really nothing but m minus n. Okay? Does that make sense? Remember? Yes. Okay, so when we do this, we substitute n with n equals to negative k, and the negation of k is just m k, and from the earlier first portion of the proof, this is nothing but m minus n, which is m minus negative k. Okay? So, if we, to make it very clear, this is m minus negative k. And how do we go from here to here? That's the result we have seen earlier right here. Isn't that interesting? So in the second case, or the third case of the proof, we are essentially using what we just proved in the first case. And in the first case, the second portion of the theorem is right here. That's what we just proved. And we were able to use that in this part. It's very important to understand here. Ym plus k equals to m minus negative k, because we just proved it. We just proved that in the first case. It's right here. Is that one? Didn't we just prove this for the case where n is positive? Yes, we just did that, and that's true by definition. So therefore, we are using our earlier result in the proof for this later portion of the proof. Therefore, this is nothing but m minus n. So once again, we prove our first portion for the third case. Now we want to do finally the last part, m minus negative m, right? And once again, n is negative. Remember, n is negative, and we already set n equals to negative k. So this is nothing but, once again, because negative n is just negative k, and this is m minus k. Oh my goodness. K is positive, and we want to prove this is equals to m plus n, right? This is what we want to prove. But now if you recall, we just proved this. Again, in this case, this is what we did. This is when n is positive in the first case. Okay? Because now n is negative, so this is nothing but m plus negative k. Okay? So, if we want to really show this is m plus negative k. And this is m plus n. So the critical thing to understand here is this step. Why this is true? Why m minus k, where k is positive, equals to m plus the negation of k? We just prove it. We prove this in our first case when n is positive right here. We just use this in the reverse order. We prove m plus negative n equals to m subtracting n. Certainly, we can see this equality from the right to the left. That's why we have this. M subtracting k equals to m plus the negation of k. We just proved that. And therefore, by definition, this is true. So, finally, we proved everything, didn't we? We proved 3 cases. For all the cases, those 2 statements are true. M plus negative n equals to m subtracting n. M subtracting negation of n equals to m plus n. It doesn't matter whether n is a positive integer or negative integer. Therefore, we prove this theorem completely. Okay, it's very important to understand why we took such an effort to prove something. If you have already learned arithmetic for negative numbers or negative integers, you know these are true. But you know they are true only because you were told they are true. Did you ever actually prove it? You probably did not. And what we just did was exactly that. And our proof was based on nothing but something that was either defined or some result we had already proven. Okay, this is the gist of mathematical proof. Every result, every statement, when you claim it's true, either it's something that we cannot prove. We say this is an axiom, or you have to prove it. And the proof must be based on definitions or axioms which are assumed to be true, or some earlier result that we have already proven. Okay, so this seems very trivial, but it does take some effort to prove they're true. And that's the beautiful part of math. If you say something that is true, you have to show it. You cannot just argue it's true. And your showing must be rigorous. Okay, so that's how difficult it is to state something, well, intuitively very easy to understand. But that's just intuition. You have to make it rigorously proven. All right? So now it's important to just remember those 2 results, because they are probably the most basic things when you do arithmetic for negative integers. Okay? So if you add the negation of a number, it's the same thing as you subtracting that number. But remember, the number here we talk about could be both negative and positive. It doesn't matter whether n is negative or positive, which we just proved, right? So the same thing for the next one. If you subtract the negation of a number, It's the same thing as add that number. And once again, this number can be either positive or negative. It doesn't matter. Okay, so those two just result are very, very important. It will accompany you for the rest of your life. That's how you deal with negative numbers. You add a number that seems to be negative, but more importantly, you may add an expression. As long as it has a negative sign for it, n can be actually positive integer or a negative integer. Okay, so it's very important to understand this. Okay, now we'll have something really interesting. The commutative law for addition over integers. Remember, we have already discussed commutative law for additions, right? But that was the version only for natural numbers. Now we expand our number system from natural numbers to integers, meaning including all the negative integers. Is the commutative law still true? Well, that's our next result. Commutative law for addition over integers. It looks exactly the same as the version we discussed last time for natural numbers. So you have two numbers, m plus n, which should be the same as m plus m. The difference this time is that m and n can be any integer, meaning that they can be negative. They are not necessarily both positive. Okay, so that is that on this number line, we want to add two numbers. Either number can be negative. So is this still true, m plus n equals to m plus m? Well, remember last time, even for natural numbers, we could not prove it. We take this as an axiom. This is even more advanced. So meaning that we will once again take this as an axiom. However, remember last time we gave this a very easy geometric interpretation, an intuitive interpretation on the number line. This is what we dealt this with. Just give you not a rigorous proof, but intuitive understanding. We have two natural numbers, m plus n. When we add them up, it's just the concatenation or seamless combination of two line segments, right? Say first one is 5, the next one is 3. When we add them, we know this is nothing but the concatenation of two line segments from 0 to 5 and from 5 to 8. As the result, we get 8 total. But if we just concatenate those two line segments, we can put the shorter one first, the second one second. We think that as long as we did not change the length of either segment, such a combination would still give us exactly the same total length for the combined segment, right? And that itself is assumed, okay? But this does give you a very good geometric understanding why this is true. M plus n equals to m plus m. When we combine two line segments, it doesn't matter the order. We put the short one first or long one first, as long as the two line segments did not change when we swap their order, relative order, the total combination should be still of the same length. And that's exactly why this can serve as a geometric interpretation. Okay, so last time that's for natural numbers. Now we the two numbers could be both negative and positive. This actually becomes a little bit more difficult to explain, but we can still do it. Let's give it a try. So essentially we are asking this question is, or I should use a red pen to make it better. Okay, is this still true? Well, to explain this on the number line, this becomes a little bit more tedious. Remember, our addition is as well as subtraction. They were all defined essentially by counting, or increment and decrement, right? This is add 1 is decrement from integer. Subtracting 1 is decrement from the same number. And our definition, once again, I want to remind you, all our definitions are right here. They cover all the cases, because that's why we took pain to give you 4 different definitions. And they cover different cases. Together, they cover every possible cases. So now, how do we understand if we swap the two numbers, when they add up, they're still the same? And either number could be negative. So this becomes repeated. We want to discuss the sign of those two numbers. How many combinations of their signs? Either number can be positive or negative, and when they combine, must be 4 combinations in total, right? So we actually have 4 cases to consider. So it'd be the first, it'd be m is positive and n is also positive, right? The second would be m is positive but n is negative. We're talking about the signs now of m and n. The third, of course, now m has to be negative and n could be positive. And finally, m is negative, but n is also negative. We want to consider all those cases in order to evaluate whether this equality relationship is actually indeed true. So let's first consider the first case. If both m and n, they're positive, what are we trying to do here? That's something we have already known, right? That's just the commutative law for natural numbers. Because, oh, by the way, if either of them is 0, this is nothing, right? So we don't consider, so we consider m and n either is positive or negative. But if any of the two is 0, this has nothing to do. For example, m is 0, this is just n. And this m plus 0, that's still n. So that must be true. So we assume neither is 0. That's why we discuss those 4 cases. So first case, check. This is good. Because it's m is already, both m and n are already positive. This becomes the commutative law of the natural numbers, which is true. The last one turns out to be also quite easy to understand. If both are negative, what are we doing here? Always consider the number line, right? If both are negative, so m is somehow here. So m is a negative 1. So this is negative m. So that means that m is on this side. M is negative, so negative m is actually it's positive. That's why we put this side here. So this is m. But n is another negative 1. So this is really becomes, think about the positive portion and of both m and n. So m plus n is really starting from 0. You count down or decrement a negative m times, followed by another negative n times, because now m and n are both negative, so negative m and negative n are positive. Therefore, m plus n is really you decrement by this many times and by this many times. But you think about this way, decrement and increment, now we understand that they are just in different directions, right? Decrement just goes toward this direction and increment just goes toward this direction. Other than that, that's temporarily put that direction aside. If you do this many decrement first, followed by this many decrement first, the total decrement must be the same as you do this decrement first, but you do this decrement second. That's once again the commutative law for natural number, right? You are talking about the total number of decrement. Remember, this is decrement, not increment. But because of the commutative law, in the natural number case, you do this many first and this many second must be exactly the same as you do the negative negation of n that many times first, followed by this many times first. And that came from the fact that we have commutative law for the natural numbers. So in other words, if you are doing this one, this is exactly you do negation of this, this is m plus m. So all we need is to find a way to convince us we can actually swap the order of the two. And if we ignore the direction, which is decrement to the left, then we can isolate the absolute value, the real number of the times of decrement we have to do. That's exactly the same as if we do increment, but increment is toward this direction. So other than the direction, we are really concerned about the total number of decrement, putting the fact that it's decrement, not increment. But if we isolate that part, we can see that we can swap the order, right? Once we swap the order, we will see this is actually m plus m, because now the two order m and n swap their order. So remember, this is not a rigorous proof, it's just an intuitive explanation. So if both are negative, m and n, we again agree this must be true. The two can swap their order. So now we have covered the first case and the second case. What if m is a positive integer and n is a negative integer? What really that means is that on this number line, if we start at 0, we first have m. So m is somehow do m increment to get m. Then we add a negative n, so we go back or go the other direction somewhere, maybe going across. So essentially we do go toward the right m times, and then we go toward the left negative n times, because n now is negative, right? But does this, so we need to do some increment first, then to do some decrement second. But does it really matter we do increment, all those increments first or second? Well, it's quite easy to see with this number line, we see that that doesn't really matter. As long as you need to go to the right and then go to the left, those numbers do not change. It doesn't matter you go to the left first or go to the right first. That's intuitively very obvious. But once again, this is not a rigorous proof. It just explains that because we can do going toward the left first or going toward the right first, as long as those numbers of steps do not change, it's the same thing. You move toward the right first, then move toward the left. Or you move toward the left first, then move toward the right. The final destination, the last point on this number line must be exactly the same. And that truly explains why this is true. Okay? M plus n equals m plus m. And finally, you have this third case. Negative, positive. M is negative, but n is positive. So that's very similar to the second case, right? Essentially, you just swap those two orders. If m is positive or m is negative, you are essentially, you need to do, I will go to the left hand side. Oops, I keep using the wrong color. No, this is good. So if m is negative, so I need to go toward the left, negation of m times, because now m is negative. Then we will go to the right n times, right? This is n. Once again, it doesn't matter, just like in the second case, it doesn't matter you do all the leftward movement first or do all the right movement first. As long as you will need to do both, your destination should not change. Okay? So that is the intuition behind this. So this is finally, this last step is the same thing. So case 2 and case 3 can be just explained in parallel, and case 1 and case 4 also kind of parallel, except the direction of the movement is opposite. Okay, so this truly, it just gives us a geometric interpretation why the commutative law is true for any integers. But this cannot be overemphasized enough. This kind of geometric interpretation, it just helps us to understand why the commutative law is true. It's not a rigorous proof. Indeed, we take this as an axiom. This is not a theorem. This is an axiom. Okay, that's, I'm sorry, it's 10 minutes over. We will pick up the associative law for addition over integers next time. I will see you Friday. Thank you. Bye.